Hello everyone and welcome back to Nunley Math. I'm your host Aaron Nunley. Thank you so much for joining me here today for the second in our video series on ratios, rates, unit rates, and proportions. As you can see from the title here today, we're talking about proportional and non-proportional relationships. We have not really discussed either of those terms yet in our unit, although hopefully you have encountered them in the past in some way or another. So to begin with, what I want to do is I want to go back to this idea of ratios that we talked about in the previous video, and I want to remind you that the same ratio can be expressed in many different ways. For example, the ratio of Frankensteins to skeletons. So if I were to put some Frankensteins and skeletons on the screen, we can create a lot of different ratios that relate these two images to one another. In this case, I asked you about Frankensteins to skeletons, and of course that would be 3 to 2 because there are 3 Frankensteins matching to 2 skeletons. But this is not the only ratio that I could create. I could also ask you about the ratio between skeletons and Frankensteins, which would then change the order of these numbers. If we were doing skeletons to Frankensteins, we would say 2 to 3. Or I could say skeletons to Halloween characters, and we would say 2 to 5. Or maybe 3 Frankensteins to 5 total, or something along those lines. There's lots of different ratios we can create, but for the sake of our discussion today, we're going to go with this 3 to 2 Frankensteins to skeletons. But suppose I were to do this. Notice that now we have 6 Frankensteins and 4 skeletons. 6 Frankensteins and 4 skeletons. Or I could do this, and I could say that there are 9 Frankensteins and 6 skeletons. 9 to 6. And you should remember from your study of fractions that if we were to look at these 3 ratios written in fraction form over here, 3 halves, 6 fourths, and 9 sixths are all actually the same fraction. They are the same ratio. In fact, if I were to take my sets of pictures over here, I can actually look here and say, well, there's a ratio of 3 to 2, there's a ratio of 3 to 2, and there is a ratio of 3 to 2. What this actually says is not just that there are 3 Frankensteins and 2 skeletons. What this ratio says is that as long as the pattern continues, every time I have 3 Frankensteins, I will also have to have 2 extra skeletons. And knowing this allows me to predict in the future, for however many times I repeat this pattern, how many of each there would be. So for example, I know that if I were to go and do this one more time, I'm going to have to add 3 more Frankensteins, 2 more skeletons, and I would have a ratio of 12 to 8. And in fact, if you were to put 12 eighths into simplest form, you would have 3 halves, just like 6 fourths in simplest form is 3 halves, and just like 9 sixths in simplest form is 3 halves. Now that may seem just a little bit obvious to you, but it's really important for us to realize that that is the definition of a proportion. When we say that 2 ratios are proportional, let me erase all that stuff off the slide. When we say that 2 ratios are expressing the same relationship, we say they are proportional. In other words, if I could take any 2 fractions or any 2 ratios that represent this same pattern or this same relationship, I could say that these 2 fractions or these 2 ratios are proportional to one another. Let's talk about what that looks like in some other examples or some other scenarios. Suppose I were to give you the fraction 1/2, the fraction 2 fourths, the fraction 3 sixths, and the fraction 4 eighths. If you've been through elementary classes, you know that if I have the fraction 1/2, I can think of it as being something like this, half of a pie. But I could take that exact same pi, and I could also cut it into fourths. And 2/4 represents the same thing, and I can't do 6 now, but I could go through here and cut this into 8, and it represents the same thing. All of these ratios are the exact same thing. And I chose this on purpose because these are easy numbers, because I want us to be able to show how we can prove that these are proportional with more difficult or more challenging numbers. Because there's lots of ways for us to be able to identify whether a set of ratios is proportional or not. The first one of those, if I can get it to show up, there we go, is to just take all those ratios and write them into simplest form. Because if you put them in simplest form, 1/2 will not simplify, but 2/4 simplifies to 1/2. 3/6 simplifies to 1/2, and 4/8 simplifies to 1/2. If you can take a set of ratios and put them all in simplest form, and they all give you the exact same fraction or the exact same ratio, then you know that you have a relationship that is proportional. That's not actually the only way, though. You could also write them with a common denominator. For example, if I were to look at this 1/2, and here again, I'm going to go ahead and clear these extra lines off the slide. If I were to look at this 1/2, and this 2/4, and this 3/6, and this 4/8, and I were to write them all as fractions with common denominators, I should be able to turn all of these into 20/4. Notice, 1/2, if I multiply the top and bottom by 12, becomes 12 20/4. 2/4, if I multiply the top and bottom by 6, you get 12 20/4. 3/6, if you multiply the top and bottom by 4, you get 12 20/4. And 4/8, if you multiply the top and bottom by 3, you get 12 20/4. As long as they have a common denominator, we can see very easily that they are the same ratio. Now, a lot of times, people find it easier to make that common denominator the simplest form, but you know, it's entirely up to you. It's nice to have multiple options. Another way would be to write them in decimal form. 1/2 as a decimal, this one right here, 1/2 as a decimal is 0.5. 2/4 as a decimal is 0.5, and 3/6 and 4/8 are both 0.5. Just in case you're unsure as to how to write fractions as decimals, just remember you always take the numerator divided by the denominator. Numerator divided by the denominator. 8 won't go into 4, so I add a decimal 0. That gives me 40. 8 times 5 is 40 with a remainder of 0. You get 0.5. Just a quick mini lesson for you right there. Here's one you may not know. It's called the means extremes property. We can use the means extremes property to prove that these are proportional as well. Notice, if I have the fraction 1/2 and I have the fraction 2/4, and I want to know whether or not they're equal to one another. I can put a little question mark over here. It would be the appropriate way to write that. If I want to know if they are equal to one another, all I have to do is multiply diagonally. 1 times 4 is 4. And multiply diagonally, 2 times 2 is 4. And then compare the products. That's the means extremes property. It says if two ratios are the same, if two ratios are proportional to one another, their cross products will be the same. Now, the real reason this works, for those that want to know, is if I multiply 1 times 4, and I also multiply the bottom times 4, this is 4/8. And if I were to multiply 2 times 2 as well as 4 times 2, I get 4/8. Just a little reasoning behind why the means extremes property works. You don't actually have to be able to do that. Also of interest, when we think about the means extremes property, the means are considered to be the 1 and the 4. The extremes are considered to be the 2 and the 2. There again, not necessarily important for you, but a lot of people are curious as to where it gets its name. Now, here's the tricky part though. In order for this entire relationship to be proportional, the means extremes property has to work for all of these, which means I also have to check 2/4 and 3/6. Well, 2 times 6 is 12, and 3 times 4 is also 12, so it works here. Then I have to do 3/6 and 4/8. 3 times 8 is 24. 6 times 4 is also 24. A few of you may have noticed that I didn't check 2/4 compared to 4/8. I didn't have to do that because if 2/4 is the same as 3/6, and I know 3/6 is the same as 4/8, then 2/4 must also be the same as 4/8. That is 4 different ways that we can spot things that are proportional. One last one that I want to make you aware of, and this one is probably brand new for everybody, it's called the constant of variation. And it goes like this. If I have 4 ratios and I want to know whether they are the same or not, what I need to do is I need to look at the numerator and compare it to the denominator. 1 and 2, 2 and 4, 3 and 6, 4 and 8. Because if this is a proportional relationship, when I take 1 times something and get 2, whatever number 1 times this equals 2, whatever we're multiplying by here is also going to have to work here, here, and here. In other words, I know that 1 times 2 equals 2. And I know that 2 times 2 equals 4. And I know that 3 times 2 equals 6, and I know that 4 times 2 equals 8. That's called the constant of variation. The constant of variation. Now, I could also do this the other way around. I could say 2 times what equals 1? Well, that's 1/2. 4 times 1/2 also equals 2. 6 times 1/2 equals 3. And 8 times 1/2 equals 4. So when we talk about the constant of variation, you could say that this has a constant of 2. The numerator times 2 gives me the denominator. Or you could say it has a constant of variation of 1/2. The denominator times 1/2 equals the numerator. Notice that 2 and 1/2 are multiplicative inverses or reciprocals of one another. Now, I know that's a lot of information. I know I kind of dumped that on you real quick all at once. We will come back and talk about this in the next slide as well when we look at things that are not proportional. And then at the end of this video, I'm going to give you some opportunities to look at some examples on your own and then see if you can make this work for you, okay? Let's talk about things that are non-proportional. I'm going to give you some easy numbers to begin with. 1/2, 2/3, 3/4, and 4/5. Hopefully you already know that 1/2 is not the same as 2/3, 2/3 is not the same as 3/4, and 3/4 is not the same as 4/5. So hopefully we just can tell by looking at that and spotting intuitively that those are not the same. But what I'm going to do is I'm going to use the same processes we used in the previous slide to show that that relationship was proportional, to show that this is not proportional. But we're going to do it a little faster this time because you've already seen it once. The first method we talked about was putting them in simplest form. Well, 1/2 is already in simplest form. 2/3 is already in simplest form. 3/4 is already in simplest form. And 4/5 is already in simplest form. Notice we were not able to get them all to match. Therefore, this is not a proportional relationship. These are non-proportional. If I went to find a common denominator for halves, thirds, fourths, and fifths would be 60. 1/2 is 30 out of 60. 2/3 is 40 out of 60. 3/4 is 45 out of 60. And 4/5 is the same as 48 out of 60. Here again, notice these do not all match. Since they don't all match, we know this is non-proportional. If I wrote them in decimal form, 1/2 is 0.5. 2/3 is 0.6 repeating. 3/4 is 0.75. And 4/5 is 0.8. Once again, they don't all match. Using the means extremes property, is 1/2 equal to 2/3? Well, when I cross multiply, notice this is 3 and this is 4. They do not match, therefore this is not a proportional relationship. Let me go ahead and check the others just to be safe. 8 and 9, non-proportional. 3/4 and 4/5, you get 15, and you get 16, again, non-proportional. Last type we're going to look at, the constant of variation. if I have 1/2, 2/3, 3/4, and 4/5. If these are proportional, when I do 1 times 2 and get 2, the same thing should happen on the other ratios. 2 times that same number should equal 3. Well, it's probably sufficient to know that 2 times 2 is not 3, and we could be done with that, but I'm going to go ahead and tell you that 2 times 1.5 is 3. 3 times 1.3 repeating, actually, I didn't put a repeating bar on that, is 4. And 4 times 1.25 is 5. Notice the constant of variations do not match. And I can do the reciprocals or inverses of those as well. The inverse of 2 is 1/2, because 2 times 1/2 is 1. 3 times 2/3 is 2. 4 times 0.75 is 3/4, or is 3. And 5 times 0.8 is 4. Again, there is no constant of variation because they're not all the same. Does that make sense? Now we've done 2 examples, one that gave us a proportional example, and then that was on the previous side. This one is a non-proportional example, but we've used the same method for both. What's nice about the non-proportional is this. In order for something to be proportional, we have to check them all and make sure they all match. They all have to match. But in the case of non-proportional, if any one of these does not match, I'm finished. I don't need to check everything. So if I were to look at simplest form and say, well, 1/2 and 2/3 doesn't work, I wouldn't actually have to go through and do the rest of these. If I can spot that 30/60ths and 40/60ths are not the same, I actually don't have to do the rest of these. And the same thing down here. If these don't match, I don't even bother with this. So it's actually easier to prove things are not proportional than to prove they are. Because if we have a pair that works, then we have to continue and check the next pair and the next pair and so on and so forth. That's a lot of words and a lot of information all at once, so I do apologize for that. But you now have 5 separate methods. Remember, on any given example, you don't need to do all 5 of these. In my class, I would expect my students to be able to choose any of these 5s, and sometimes I would require them to use a specific one of these, but they don't have to use all 5 every single time. So if I were to give you an example like this, this is a ratio of packages to Skittles. So when I buy 1 package of candy, it has 25 Skittles in it. 2 packages have 50, 3 have 75, 4 have 100, and 5 have 125. Notice I didn't write these as fractions, I wrote it as a table this time, but you can still see the ratio. 1 to 25, 2 to 50, 3 to 75, 4 to 100, 5 to 125. I would like for you to pause the video and see if you can determine if this is proportional or not proportional, non-proportional, using any one of the 5 methods that we showed you on the previous page. Then what I'd like you to do is I'd like you to restart the video and check to see if your answer matches mine. I'm going to assume that if you wanted to do that, you already have. Again, you could have chosen any of the 5 methods. In this case, I happen to choose putting these in simplest form because when I look at these, I can very easily simplify 2 over 50, 3 over 7. These are all pretty easy numbers to simplify. So I happen to notice they all simplify to 1 over 25. So I can tell you that this one is proportional. How'd you do? Again, if you had turned those into decimals, you would have got, what is that, 0.04, I believe, something like that. If you had looked for a constant of variation, you would have got that K was either 25, because packages times 25 gives you Skittles, or you might have gotten the other way around, the reciprocal of that, which is the number of Skittles times 1/25 gives you the number of packages. Or you could have gone through and done the means extremes property. Again, it's entirely up to you. You get to pick. Here's a second example. This is the amount of flour in a recipe compared to the amount of salt in a recipe. Take a second, pause the video, try it on your own. I'm going to keep going, assuming that you have already done that. In this particular problem, I'm looking at this. This is a little messy. I see some fractions inside of my ratio. I don't like that at all. So I'm not going to do this in simplest form. Instead, I'm going to write these as a common denominator. 1 over 1 could be written as 6 over 6. 3 halves over 2 could be written as 3/6. And at that point, I can see this is non-proportional, and I'm not going to bother doing the rest. Some of you may have found it easier, instead of turning 3/2 over 2 into 3/6, you might have found it easier to skip this one and tried the 2/3 and made that 4/6. Because there again, you could see that 6/6 and 4/6 are not the same thing, meaning you would not have to bother with the rest of them. Use a little bit of that logic to help you. You don't necessarily have to do these in order. All you have to do is find the ones that don't match. Here's another one. Pause the video, try it on your own. I'm going to assume you've done that and you're just here checking your answer now. This time I'm just going to use constant of variation. When I look at this, it's very easy for me to see that I'm multiplying by 6 every time. 3 times 6 is 18, 4 times 6 is 24, 5 times 6 is 30, 6 times 6 is 36, 7 times 6 is 42. Or if you want to do it the other way around, 18 times 1/6 is 3, 24 times 1/6 is 4, all the way down. Again, because this is proportional, it's very important that I don't just check a couple sets, I have to check them all. Because you know me as a teacher, sometimes I'm mean and I make them all match except for the very last pair, and then people who don't check all the way end up getting them wrong. That's just how I roll. I'm like that sometimes. Here's another one. Pause the video, try that on your own. I would do this with the means extremes property. Notice when I cross multiply, 10 times 2 is 20, and 1 times 18 is 18, so I instantly know this is non-proportional. How about this one? I'm going to turn them to decimals this time. 10 divided by 2 is 5, 20 divided by 4 is 5, 30 divided by 6 is 5, 40 divided by 8 is 5, 50 divided by 10 is 5. These are proportional. How about this one? I'm going to do this finding the constant of variation because the numbers are pretty friendly. I'm trying to see what the top number times what gives me the bottom, or the bottom times what gives me the top. Hopefully you can see that the constant of variation is 20. If I have 1 tray times 20, it's 20 brownies. 2 times 20, 40. 3 times 20 is 60, and so on. Again, make sure you check them all, and also be aware that the multiplicative inverse or the reciprocal would also work. You getting there? All right, let's keep going. Find the constant of variation and use it to write an equation. The constant of variation k can be found by dividing one item by another. Let's talk about that a little bit. In this case, I've given you a set of ratios. It looks like it's comparing ounces to cups, ounces to cups, ounces to cups, and so on and so forth. I specifically tell you here that you have to find the constant of variation. That's one of our 5 methods, which means I'm trying to say the top number times what equals the bottom number, or the bottom number times what equals the top. Can you figure that out? Hopefully you didn't have too much trouble with that. Here's a way I do that. 8 divided by 1 is 8. 16 divided by 2 is 8. 24 divided by 3 is 8. 32 divided by 4 is 8. And 40 divided by 5 is 8. In other words, my constant of variation is 8. This is a quick and easy way. If you can't just look at this very fast and see, oh, they're all times 8, if you do the top divided by the bottom, it will give you the 8 every single time. If it doesn't give it to you every single time, it is not the constant of variation. So we found k. But notice the second part of this. It says, use this to write the equation. In other words, once I realize that the constant of variation is 8, I need to write an equation that compares ounces to cups. Because I can see that if I have 1 cup and multiply it by 8, it gives me the ounces. If I have 2 cups and I multiply it by 8, it gives me the number of ounces. In fact, no matter what the number of cups is, if I multiply it by 8, it's going to give me the number of ounces. So what I'm going to do then is just say my ounces is 8 times my cups. Notice I did the constant of variation times cups to get the ounces. Now, same thing over here. Suppose instead of doing it like this, I decide, hey, I'm going to go through and take the 1 and divide it by the 8. 1 divided by 8 is 1/8. 2 divided by 16 is 1/8. 3 divided by 24. All of these give me 1/8 if I do the bottom divided by the top. Because of that, I could say the constant of variation is 1/8. The ounces times 1/8 gives me the cups. You see, there's really two different ways I can write this equation. Cups is 1/8 times ounces, and ounces equals 8 times cups, both using a different constant of variation, but both equations meaning the exact same thing. In other words, if I gave you a specific number of cups and you plugged it into this equation, you would get the same answer as if you were to plug it into this equation. This is two ways to write the exact same relationship. In fact, in our algebra unit, when we talk about solving equations with variables, we will use the same principle a lot. The fact that two equations can mean the same thing even though they look different. By the way, instead of constant of variation, you'll notice that this time down here I use the word constant of proportionality. It's the same thing, so don't worry about it if you get a different word. Here's what I'm going to recommend you do. I'm going to ask you to determine if each of the relationships I'm about to give you is proportional or non-proportional, if I could talk. If they are proportional, then you must find the constant of proportionality, and you must write the equation. So if we come up with an answer that's proportional, then we have to do two extra things, which means if we can show they're not proportional, there's a lot less work to do. Here's your story. Take a second, look at that, see if you can find out whether it's proportional or not, and figure out which method you want to use. I'm going to suggest, since we know we're going to have to use the constant of proportionality anyways if it's proportional, I would suggest using that in order to determine if it's proportional or not. In other words, the top number 1 times what equals the bottom number 50. Well, I can see 1 times 50 equals 50, but I can also see that 2 times 70 does not. This is not proportional. Notice again, in my example down here, you'll remember I told you if you can't spot that right away, just take the 50 divided by 1, the 70 divided by 2, and see if when you divide they give you the same thing. This is non-proportional. Here's a second example. Does this have a constant of proportionality? Well, let's see. If I take the 8 divided by 1, the 16 divided by 2, the 24 divided by 3, wow, that's a typo, 24 divided by 3, or the 32 divided by 4, wow, that's terrible. I do end up with an 8 in all instances. So this does have a constant of proportionality. It is proportional, and your k is 8. Can you write an equation using the 8? Well, hopefully you realize that the number of legs is 8 times the number of spiders. Again, if you had done 1 divided by 8, 2 divided by 16, 3 divided by 24, and 4 divided by 32, you would have got the reciprocal of all of these, which would have given you a k equals 1/8. That would also be an acceptable answer. K equals 1/8, because the number of spiders is equal to 1/8 times the number of legs. Try this one on your own. Well, let's see. If I'm looking for the constant of proportionality, 5 divided by 3 is 5/3. You guys thought you had to turn that to a decimal, didn't you? 10 divided by 6 is 5/3. 15 divided by 9 is 5/3. 25 divided by 15 is 5/3. So yes, this is proportional. The constant of proportionality is 5/3 because the number of dogs is equal to 5/3 times cats. You could have also said the constant was 3/5 and the cats was equal to 3/5 times dogs. Is that getting easier? I hope so. One more. You're trying to find a constant of proportionality. 20 divided by 4 is 5. 35 divided by 7 is 5. 40 divided by 8 is 5. 55 divided by 11 is also 5. So yeah, it is proportional because you have that constant of 5. The number of sticks is equal to 5 times the number of packs. Whew. Doing okay? All right, let's put it all together now. A recipe for jelly frosting calls for 1/3 cup of jelly and 1 egg white. Is the number of egg whites used proportional to the cups of jelly used? And if so, find K and give an equation to model the situation. Notice there are 4 steps here given to you. Make a table of values, decide if it's proportional, and if it is, find the constant proportionality. If it's proportional, give the equation relating the items. So up until now, I've been giving you the table. This time you've got to fill it in yourself. So let's take a look and see. 1/3 cup of jelly and 1 egg. So if I put 1/3 a cup of jelly into my recipe, I know I'm going to need 1 egg white. Suppose I want to double that recipe and get extra jelly frosting. Well, now I've got 2/3 cups of jelly and 2 egg whites. If I do it again, I get 1 whole cup of jelly and 3 egg whites. And if I do it again, I get 4/3 cups of jelly and 4 egg whites. The question is this proportional? Is there something that the bottom number can be multiplied or divided by to get the top number? Well, let's see. 1 divided by 1/3 is 3. 2 divided by 2/3 is 3. 3 divided by 1 is 3. And 4 divided by 4/3 is also 3. There is a constant proportionality here. It's the 3. Your egg whites is equal to 3 times the cups of jelly. You could have just as easily have done this the other way around. 1/3 divided by 1, 2/3 divided by 2, 1 divided by 3, 4/3 divided. You could have done that. If you had done that, your constant proportionality would have come out as 1/3. And you would have said the amount of jelly is equal to 1/3 of the egg whites. One extra step, because you had to create your own table, make sure you're careful in doing that. Some students struggle to get that done correctly, but if you're conscientious, it shouldn't be too bad. I've got one more of these for you, and then we're going to call it quits for the day. Uptown Pizzeria sells medium pizzas for $7 each, but charges a $3 delivery fee per order. My students sometimes get confused because this $3 delivery fee is on the order. It is not on every single pizza. So if you have pizza delivered, you're going to pay for the pizzas and you're going to pay the $3 once. Is the cost of an order proportional to the number of pizzas ordered? If so, find K, your constant of variation, and give an equation to model the situation. I'm going to recommend that you pause this, try it on your own, and then restart the video to see if what you did makes sense. I'm going to go ahead and work this out, assuming you've already done that. If I order 1 pizza, I'm going to pay them $7 for the pizza, but I'm going to pay them $3 extra for delivery. It's going to cost me $10. If I buy 2 pizzas, they are $7 each. That's $14 plus a $3 delivery fee. That's $17. 3 pizzas is $21 plus the delivery fee makes $24. 4 pizzas is $28 plus the delivery fee is $31. The question is this proportional? Well, let's see. 10 divided by 1 is 10. But 17 divided by 2 is 8.5. At that point, I can already see this is non-proportional and I'm finished. Sometimes my students get stuck because they're like, oh, well, I have to have a constant proportionality and I have to give an equation. No, those are conditional. If it's proportional, you have to do those things. If it is non-proportional, you're done. So we love it when our homework comes out as non-proportional because it's way less effort, way less work, way less steps for us in order to get this right. Hopefully that has not been too overwhelming for you. I think once you see a couple of them, it should start to make sense. If not, definitely go back and re-watch a couple minutes towards the beginning to make sure you understand what your methods are. Make sure you understand why the constant proportionality can be 2 different values, just in case you get a different number than one of your classmates who might be working with you. As always, I do appreciate you taking the time to join us here today. I do appreciate the time we get to spend together. I wish you the very, very best of luck. You guys take care of yourselves, all right? Until the next time, bye-bye.